Welcome back to day 2 of our Plan Z, Simple Machines, Wheels and Axles and Pulleys. Just as a refresher course of what we learned last time, we learned about first-class levers, like seesaws, where the fulcrum is in the middle of the effort force and the resistant force. Okay, that is a simple way of saying if I'm pushing here, then my weight would be, oops, this is backwards. My weight would be here, also pushing down. Okay? That's a first-class lever. Then we have a second-class lever where the resistant force is in the middle with my effort force on the outside. Okay? Just like a wheelbarrow. The third-class lever, so this is effort, this is resistant. My third class lever is the opposite. My resistance is on the outside, and my effort force is in between the fulcrum and the resistant force. That is like tweezers or a stapler to get more force out. This third class levers always have a mechanical advantage less than 1. Second class levers always have a mechanical advantage greater than 1. And first class levers can have them in anywhere between. They could be less than 1, they could be greater than 1. It just depends on the distance between the forces in the fulcrum. And we're about to talk about that right now. So, without further ado, shush now. Let's talk about moments. So, come on. You can do it. There you go. Moments. Moments are the rotational equivalent of work. As a refresher course, work is equal to the force that we're applying to some object times the distance that object travels. Okay? So, if I'm pushing something along, okay, if I'm pushing it this way, the distance where it goes times the force I applied will equal the amount of work being done. Usually foot-pounds, okay, or inch meters, or I mean that would be weird because those are metric in English, but it's some unit of distance times some unit of force. Usually foot-pounds. Now, moments are the same thing, except I am using, notice it's the exact same formula. Distance times force or force times distance because the associative property, you can flip-flop them. Distance times force is equal to a moment, right? The way I always remember this is work, when you turn it upside down, because I'm rotating it, becomes a moment. Ha-ha! Yeah, that's fun, right? All right. So, the exact same equation, except here, how many moments do I have? I'll give you a moment to think about it. In my first example, I have one work scenario. In this scenario, I have two forces and two separate distances. So how many moments do I have? That's right, I have 2 moments. Congratulations. So, we can talk about what to do with those 2 moments in a moment. A force that produces or tends to produce rotation or torsion, that's called torque. Okay? It's basically the rotational equivalent of force. So, this moment we can calculate, okay? We have a force here, and we have a distance at which is being applied to the fulcrum here. So, how do I calculate those? I take my moment is equal to d times f. So I get 5.5 inches times 15 pounds, which gives me 82.5 inch-pounds for the moment. Okay? That's for effort. Notice, this is the effort. How do I know it's the effort? Because it tells me. It's that simple. Okay? If they didn't tell me, it would be me applying it to a scenario. Okay? So, when the sum of all moments on a lever equals 0, the lever is in rotational equilibrium. Now that is a really fancy way of saying this. When the sum of all moments is equal to 0, then we are in rotational equilibrium. Now that is a really fancy way of saying this. Let's say I have 2 moments like I did before. Okay? I have this resistant moment and this effort moment. Okay? I have 2 moments. I'm going to sum them together. I'm simply going to add them together. This symbol is a fancy way of saying add everything up. Okay? It's called sigma. It's a fancy Greek word or letter that means to add. Okay? So I'm going to take the sum of everything. So I got moment E plus moment R. And if they equal 0, what's that lever doing? Well, nothing. It's not moving at all. It's an equilibrium. Okay? It's not moving. Both sides are equal. Now, this could happen in a couple of different ways. The forces could be equal, in which case the distances have to be equal. I'll show that in a minute mathematically. And if the distances are equal, then the forces have to be equal. If not, then if the force is proportionally less, then the distance has to be proportionally less. And we can show that in a moment. But there's one key thing I want to show you with this equation. If I want to solve this for MR, for the moment of resistance, notice what happens. How do I get MR by itself? Well, I would simply subtract it. So I get the ME is equal to the negative of MR. Why is that negative for? In math, we know the negative goes in the opposite direction for the number line, right? If I have 0 is my, let's say, fulcrum or middle, and I have positive 2. If I had a negative 2, that means I'm not going to go this direction. I'm going to go the opposite direction. I'm going to go negative 2. In physics, it's the same thing. I'm not going in any different mathematical quantity or magnitude, as it's called in physics. The distance here is a magnitude of 2. I'm simply going the opposite direction. That is what this symbol means. Notice that if my effort force was to go unencumbered, this would spin all the way around, right? In order to combat that, my resistance must spin in the opposite direction. Okay? So far, so good. Why did I choose my resistant force to be negative? Well, that's a great question. Let's assume that it's just simply a free-falling body or just something at rest, which means it's being pulled down by gravity, right? So if it's being pulled down by gravity, in physics, gravity is always negative. It just is, just a standard in physics. So my resistant force tends to usually be negative. I could have said the opposite. I could have said my resistant force is the positive version and my ME would be negative. It wouldn't change the equation at all. Okay? All right. So, oh my gosh, that's a whole lot. I think I covered that pretty good. You can go back and look at it if you like. Here. You can pause this video and see that if you would like. Just fancy ways of saying what I've said. All right. Lever, moment, calculation. So here I have a system. Okay? I have a force unequal to the force on the other side. Notice is further away. Since the force is further away than the other force, my effort force is further away than my resistant force force must be closer. In fact, exactly a measurement closer. And that measurement can be figured out mathematically. If we have this measure, this moment is equal to ME, is equal to this moment, okay? Maeve. Sorry, guys. My daughter is playing and is in a very yelly mood tonight. So, I have my moment, and I have my effort force moment is equal to my moment of resistance, okay? And then what I always do is anything that's moving counterclockwise, that is this direction, I make negative again, which would make this positive, okay? So I have two positive situations because this distance should be positive. To help us kind of organize it, if you made it negative, it wouldn't change anything. I would know it means it's the opposite direction of 5.5. Because if this is 0, then this would be positive, the way we set it up, and this would be negative. So if you got a negative number, I wouldn't be upset. I would understand what you're saying. So, but to make everything equal and simple without negative values, I just tend to double negate, but that's not important. So, my ME can be broken down into force times distance, which is equal to force times distance. Now I have to carry the E. I got to carry the R so we don't get confused. FE I know is 15 pounds. Okay, that's here. dE, I know, that's my distance of my effort force to the fulcrum. That's 15 or 5.5. Okay. I also know the force of my resistance, right? That is 32.66 or 32 2/3 pounds. Remember to use the variables. Very important to use variables. Okay. And then I don't know the distance to the fulcrum from that resistant force. So I can solve for it. So just like a normal equation, I would multiply 15 times 5.5 to get A2. We solved for that already. It's going to be equal to this value, and I just simply divide by it here. And then I know in order to reach an equilibrium, which is to say that the sum of all the moments equals 0, or that both moments are equal to each other, that resistant force must be 2 1/4 away from the fulcrum, or 2.25, or 2.250 thou for Harrison, who's also in the precision machining class. Okay? Yeah. Okay. If I was to let this system go, right? Let's see. Hold on. Where's this going? No, I don't want to talk about the circle. Don't worry about the circle. Let's just talk about the distance. This is a really fancy way of trying to get you to have the arm length, but basically my resistance is a radius of a small circle, and my effort is a radius of a big circle. Okay, so this would be RE and RR. Okay, and that is to solve for this IMA. Because just like for the any other system, we have to have the ideal mechanical advantage based on the distance from anything else. And we're just going to use the same distance we did last time. So my DE here would be 5.5. My DR would be 2.25. Okay? And I would just divide them. That's it. Let's see, what is it? 5.5? 5.5 over 2.25 to figure out my ideal mechanical advantage. And I should put the inches in here. Notice the inches divided by inches cancel out, which gives me no units. That's very important for mechanical advantage. Mechanical advantage has no units. There are no units. It is just a ratio. Okay? So don't worry about that. Actual mechanical advantage on the other hand is based on the forces applied. Okay? So ideal mechanical advantage was based on the distance. Actual mechanical advantage is based on the actual forces applied. Okay? So, here would be 32 over 16, which would give me an actual mechanical advantage of 2 to 1. Pretty simple. My IMA here, on the other hand, would be 5.5, would be my DE over DR. DE, you gotta be very careful when you use this. DE over DR, which would be 5.5 over 2.25. Okay? Which would give me 2.44 over 1. Candy Maeve. Thank you. So, notice, one of them is bigger than the other. Which one is bigger? That is correct. IMA is bigger. Now, why would the mechanical advantage measured by distance always, and this is true, always be bigger than the actual mechanical advantage, which is measured by forces? This was your assignment last class, and I'm going to go ahead and give you the answer now. I want everyone to sit here at your computer and just like pretend you're cold. Take your hands and rub them together. Okay? Rub them together. You can hear it. I'm doing it. Okay? Notice, what can you hear? Well, I can hear the sound of my hands rubbing together. Okay? What else do you feel? Well, my hands are getting warm. That's right. So, where is the energy from rubbing my hands being lost? Because I should, ideally, have all the energy from my muscles on my right side and all the muscles on my left side equal each other. But I'm not. I'm losing energy. I'm losing energy from the sound, and I'm losing energy due to friction through heat loss. Same here. There is friction right here that is being lost through sound or heat or some unknown drag force that we can't calculate for because we don't have the kind of equipment necessary to calculate drag of air resistance. For some reason, we have lost 0.44 through mechanical advantage. Okay? The IMA in an ideal frictionless world will always be higher than the actual real-world measurement of a system. Okay? Even if you go to space, you will lose energy due to friction. Okay? There are photons coming off the sun. If I'm just drifting through space, the photons hitting me will slow me down. If you don't believe me, look up solar wind sails. There are actually spacecrafts being powered now through solar wind. The radiation and photons being let off by the sun will be caught in this big copper sail, and they'll actually accelerate the spacecraft through the cosmos. Solar wind sails are a really cool read if you get the chance. Why is IMA larger than AMA? That's why. So now, since I have something larger than something else, just like if you got a 9 out of 10 on an assignment, we could come up with a percentage. A 9 out of 10 would be, obviously, 90%. Okay? This equation is simply saying 9 divided by 10 is 0.9. So I'm going to multiply that by 100 and get a percent. That's how you get percents, right? So this will tell us how efficient our system is. Okay? So we're going to take our AMA, which is 2.1. If I put that in a fraction, it would be 2 over 1. And if I wrote that as a decimal, it would be 2. I'm going to take that and put it over my IMA. If I wrote that as a fraction, it would be 2.44 over 1. And if I wrote that as a decimal, it would be 2.44. Pretty simple. So I'm going to take 2, I'm going to divide it by 2.44. And that is going to give me a decimal value that I will multiply by 100, which is 82%. So 2 divided by 2.44 is 0.82 times 100 is 82%. Our lever system that we just calculated for is 82% efficient. Okay? No machine is 100% efficient. Why? Friction, sound, drag. We don't live in a perfect system, guys. We just don't. We can try. We can make an ideal system, but it'll never function at 100%. Next time we'll get to wheel and axles, which are basically just levers that have gone crazy and won't stop. Yeah.